Before we get started, I just wanted to take this opportunity to say thanks to all our viewers and subscribers. We've now reached 100,000 subscribers and we have some exciting future plans which wouldn't be happening without all of you. More on this in a future video. A few years ago, Alistair made a reproduction of the Antikythera mechanism, which is a geocentric orrery. The mechanism behind the Antikythera mechanism is astoundingly complex. I wanted to go the other way and have a go at building a simplified heliocentric model, but the challenge is miniaturization. The model is around 20mm long, and to my knowledge, this is the smallest standalone orrery in the world, excluding watches with complications. But let me know in the comments if you are aware of a smaller one. This orrery models the relative motions of the Sun, Earth and Moon. In this design it takes 6 gears to achieve the correct gear ratio and directions. The Moon must orbit the Earth 12.4 times each time the Earth revolves around the Sun. Here I begin machining the largest wheel. Once the brass blank is turned, I position a 1mm diameter milling cutter using a centering microscope mounted in the headstock of the watchmaker's lathe. To do this, I had to remove the workpiece from the spindle, so it's important to check it's still accurately centered when I mount it back in the lathe. Once positioned, I can remove the milling spindle and cross-slide assembly to slide back into place once the wheel bore is drilled. With the dividing attachment and overhead drive, I mill the gear spoke pattern into the blank. This reverse taper spoke pattern is unconventional, but enables easy machining on a watchmaker's lathe without moving the centre height of the milling spindle. Now it's time to move on to cutting the gear teeth. For this project I'm using commercial gear cutters. Due to the scale here, we need to pay particular attention to the setup. I check every aspect such as cutter concentricity and alignment before locking the cross slide securely to ensure it doesn't move when we begin machining. I gently move the cutter until it just makes contact with the external diameter of the wheel blank. Here you can see a small scratch in the blue, so I can be confident the cutter is making contact. I move the milling spindle by the correct amount to generate the correct tooth form, and then go ahead and mill the teeth. Although it looks tedious machining each tooth individually, the milling operation itself is actually quite quick, taking around 20 minutes. Now the wheel is parted off. Parting off leaves a notoriously rough surface and should either be lapped or faced off. I've discovered that a great way to position the wheel for gripping in the collet is to guide it with a drill bit and chuck. I can now face off the wheel and deburr the component using a buff file. Using the watchmaker's bench micrometer, I check the wheel is at target thickness and is parallel. The other wheels are made using the same approach. Here I part off the wheel that's concentric with the sun. The wheel I'm machining here is concentric with the Earth. It's only 6mm in diameter, but the tricky bit with this component was the off-centre hole to accept the Moon. To provide clearance between the Earth and the Moon, I had to drill this as far away from the centre as possible, and you can see the hole nearly intersects with the root of the tooth. This wheel also has a little pedestal, so it's at the right height to engage with the big wheel I made earlier. This will become apparent when we get onto the assembly. This is the smallest wheel in the mechanism. It's 3mm in diameter and has 19 teeth. With the wheels now made, that leaves us with the pinion to complete the gear train. The pinion has 8 leaves and is less than 1.5mm in diameter. For perspective, the diameter of the pinion is similar to the wire diameter of a paperclip. I machine the pivots down to 0.5mm in diameter, and then machine the teeth using the same approach I use for the wheels, but in this case I use multiple passes to form each tooth. I won't go into detail here because making a pinion is an involved and interesting process, so I will reserve this for a future video. I stake the pinion to the large wheel.
Want to delve into the science behind orreries like this? Check out this video's sponsor, Brilliant. Brilliant is an interactive platform where you learn by doing, with thousands of interactive lessons in maths, data analysis, programming, and AI. Brilliant helps you build real knowledge in minutes a day with fun lessons you can do whenever you have time. Forget dull lectures, Brilliant builds your knowledge from first principles through hands-on problem solving. If you've been enjoying this video, be sure to try Brilliant's Scientific Thinking course, which takes you on an interactive tour of our physical world. You'll engage with key scientific principles and theories, from simple machines like gears and pulleys to Einstein's special theory of relativity. It's perfect for learners of every level, no matter your math skills. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/CronovaEngineering or click on the link in the description. You'll also get 20% off an annual premium subscription.
So that's the gear train complete, and now it's time to have a think about what we can do for the celestial bodies. There's a Japanese company that makes these groovy glass-headed pins, which is perfect for Earth. These silver-plated, ball-headed pins would make an ideal moon. For the Sun, my first thought was to machine it from brass, but I wanted to differentiate it from the rest of the mechanism, so I decided to use these 8mm ball bearings to make a silicone mould which I could then use to cast the Sun from resin. Before I poured any silicone, I applied some release agent to help demould the silicone. I doubt this is necessary, but better safe than sorry. Once I had poured the silicone, I placed the pot into a vacuum chamber for degassing. Once I had the mould, I mixed up some suitable resin and used a small amount of yellow tint for colouring. I also used a touch of orange. My hope was by not completely stirring the orange in, the Sun would have some non-uniformity to its colour. This didn't work out in practice, and the theory for this is that the resin was too slow curing, so the colour had too much time to diffuse. Upon demoulding, the Sun looked pretty terrible. It looks like the silicone didn't degas properly, and I thought it was a bit of a stretch arguing the spikes looked like solar flares. Thankfully, my trusty watchmaker's lathe saved the day, and the casting was salvaged with a graver. I decided to leave the finish slightly matte to help hide the pin on the inside. It's nearly time to move on to the assembly, but there are still a few things to finish first. Most of the gear train is supported by individual screws, however this was not possible with the pinion and large wheel assembly due to the small size of the pinion, so this is supported with a bridge. The bridge itself is supported by pillars which are turned on the watchmaker's lathe. We also need a substrate to which the mechanism can be affixed. I make this from brass plate, which I first rough out with a jeweller's saw and then finish with files. To mount the gears, I made hollow screws. The holes through the centre of the screws accept the pins supporting the celestial bodies. The pins are a push fit, so the mechanism can be easily disassembled. I wanted a base to support the Orrery, and I thought the pencil worked well for the beam Stirling engine project, so I used the same approach here. I applied wash oil to the various bearing surfaces as the mechanism was assembled. One gear pair had to be fixed relative to each other, which I did with the staking tool. The bridge pillars were screwed in place using brass face pliers before fitting the pinion and large gear assembly and supporting bridge. The final gear was screwed into place and the celestial bodies were slotted into their corresponding holes. As we push the arm around, the Moon orbits the Earth 12.4 times for each arm revolution. The Moon rotates counterclockwise as the Earth is pushed round also counterclockwise. Of course, in reality, the orbits are quite complex, and this model is heavily simplified. Perhaps in the future I will revisit the project with a more advanced model. Thanks for watching, and I'll see you in the next video.